Welcome, everyone, to a very special episode of the Global Guessing Weekly Podcast, the podcast on all things geopolitics and forecasting. Today, Andrew and I are joined by two very special guests, Ville and Marat, who are the two lead authors on the BIN Model of Forecasting paper, one of our favorite papers of this year that talks a lot about where forecasters make their mistakes and the sources of their error. We are really excited to have them on the show today to talk about the paper, what their main findings are, as well as diving into what the implications of their paper are in terms of individual forecasters, as well as crowd aggregating forecasts that you would get on websites such as Metaculus. Both of our guests are very interesting, and so we'd love for them to introduce themselves and give a little bit of their background in terms of forecasting, as well as sort of how they got working together on this paper on the BIN model of forecasting.
Thanks a lot, Clay. Should I go first?
Yeah, that'd be great.
So my name is Ville Satopää. I'm an assistant professor at INSEAD in the operations group. My background is actually in statistics. So I did my PhD at the Wharton School, graduated about 5 years ago. But I would say maybe more than that, maybe about 10 years now, I've been closely collaborating with Barbara Mellers and Phil Tetlock. And this paper really is just one of the sequence of papers that we have collaborated on. And it started off a couple of years ago now. I remember I had a chat with Barb, and she was showing me some predictions and how there was a lot of disagreement. And she said to me, Ville, look, there's a lot of noise in here. And I remember I said that, well, how do you know it's all noise, right? Maybe they're also disagreeing because they simply have different information, right? And then this led into more and more discussions, and eventually we started thinking about a model. And I remember I made a comment that, look, there's this very bright student at INSEAD at the moment. His name is Marat. What do you guys think? Should we ask him to join us? And well, there it is. That's how the paper started off.
And for my part of the story, so my name is Marat Salikhov. I'm currently a postdoc at Yale School of Management. I got my PhD from INSEAD, and I have a little bit of a reverse of the situation that Ville has. So Ville has his PhD in statistics and his main research interest in statistics, but his appointment is in operations. But I have my PhD in operations, but most of my interests are now in the area of statistics and forecasting. How did I come to this situation? Well, in my first year at INSEAD, I started pondering some of the fundamental questions of operations. And I think one of the main questions in operations management is how much of a product to produce or to order from a manufacturer, right? And it seems that when you consider new products, for example, say fashion goods or kind of fashion goods, or home decor, or flowers, sometimes you face a lot of uncertainty in the demand for a given product. And it's really not clear how to estimate this uncertainty and how to forecast this demand. And it's somewhat similar to what happens with geopolitical events. So geopolitical events are one-off. It's not really clear what models to use here, and we rely a lot on experts. The same story is true for new products, right? You have to rely on experts, at least to some extent, to produce the geopolitical forecasts. So I started thinking about this problem, and I started working out some methods that could potentially combine the sales data for past products with expert inputs and produce the probabilistic forecasts. And along the way, I started studying the literature on experts, and I found that Ville did a lot of interesting work on information diversity across experts, on noise, on aggregation. And I became just very interested in Ville's work, and Ville was a student, PhD student at Wharton at this point. I started discussing it with my advisor, and somehow next year, Ville went for a fly out to our school, and he got hired by our operations management department. But at this point, when I was a PhD student at INSEAD, we were not working closer together. So I was focused mostly on other projects. But when I was close to my graduation, basically around my graduation ceremony from INSEAD, Ville approached me with this very interesting project. I was really happy to have this opportunity because I understood Ville's work very well. And then I was able to, I guess, to move this project forward, to come up with ways to estimate the model, to interpret the conclusions, and to link it maybe to a wider body of literature on decision-making forecasting. So that's how we came together and formed that team. And I would say I was very happy with us working together. So we complemented each other very nicely, and we were able to progress at a very fast pace.
You make such an interesting comment about, forecasting just outside of geopolitics when it comes to sales and inventory within management. And, obviously at Global Guessing, given the name, we focus mostly on geopolitics, but forecasting really, is in almost every single industry and very important. And, the example you give right there with sort of sales and product and inventory is sort of really resonant right now, looking at a lot of the sources of the recent inflation in the United States seems to have been due to poor forecasting in terms of when reopenings were to happen, when, businesses would sort of need all that inventory. And if they had sort of proper forecasts, maybe there was too much noise or bias. And I want to talk about all those terms because we're sort of throwing them around and all of our listeners might not be aware of the difference between bias and noise. But I think that really sort of brings up a
Yep.
really great observation, and we can hopefully circle back to that. I think it would be really useful right now if you gave our listeners an overview of what the bin model of forecasting is, like what is bias, what is noise, what is information, and how do all of these sort of interact with one another when someone is creating their own forecast.
Yeah, let me take that one. So let me first explain what bias, information, and noise are. So that's what the bin model really stands for. So bias, you can think of it as a systematic error. So in this paper, we are only considering probability predictions of future binary events. So this could be, what's the probability that this particular candidate is going to win the elections, for instance. Now, what is a bias? Bias is a systematic over or underestimation of probabilities. So for instance, you can consider predicting many events over time. And suppose after the fact, you find out that 20% of them actually occurred. Now, then you can calculate the average of your predictions. Now, suppose that was 25%, so 0.25. That would mean that you were systematically overestimating probabilities. It would have a positive bias. Of course, it could be the opposite as well. Maybe the average was 15%. Then you would have a negative bias. So bias is just kind of a systematic shift up or down. Now, what is information and noise then? To understand this, we need to think about these predictions that we have made for the many events over time, right? So ultimately, you're going to end up with lots of predictions. There's variability in that. And we will decompose this variability into what we call information and noise. In particular, when we consider the variability, some of it will actually correlate with the outcomes, right? And this is helpful to us. This will actually tell us something about what is going to happen, right? And this is what we call information. Now, not all of that variability will, of course, correlate with the outcome. This is not helpful for us, and this is what we call noise. These are the three components. Now, what does the bin model do? It is a model of two groups of forecasters that are separate, one that we call the control group and one that we call the treatment group. And it's a joint model of these two groups. And for each of the groups, it will estimate their levels of bias, information, and noise. And we do this in a sort of a joint way so that we can make comparisons between the two groups. So that's sort of the high-level gist of the bin model.
And then sort of taking like one step into that to dig a little bit deeper, particularly into information and noise. In the paper, you say that, forecasts are determined that there exists sort of this universe of signals out there that have these values ranging from, negative to positive infinity. And that, well, I don't know if it goes to infinity, but negative to positive, and that the sum of those signals will indicate whether or not an event happens. If the total sum is negative, it doesn't happen. If it's positive, it does happen. And perfect information would be sort of being able to know what all of those signals are going to be, and that you operationalize noise as being that there exist these signals, but then there's also like fake signals. So if you had like a bucket of pool balls, some of them will have numbers, some of them don't. Your signals are ones that have numbers, your noise are just sort of blank balls. And if you happen to take out a blank ball and actually say this one actually has a number on it, I'm going to put it into my forecast, you're increasing your amount of noise. And if you're only taking out the good ones, you're just increasing your information. Is that a correct summary in terms of how both of those work?
Absolutely. And I think the challenge really occurs when you looking at one of these noisy bits, like a noise, but you interpret it as true information, right? And that will then change your prediction, but not in a justified way. And that causes noise, right? So you could think of, for example, if some kind of a fake news, right? I see it on the internet, I believe it's true. And because of that, I'm going to completely change my prediction. But that's not, that wasn't a justified move. That would be noise, right?
Yeah, so then when we look at all of these sort of differences, so you have bias, which is just generally, being wrong in one direction, so you'll always just be a little bit, the status quo change, it's more likely or less likely across the board, versus sort of taking in false information into their forecast and becoming noisy. How do all of those sort of relate to error? Is forecasting error coming primarily from noise, from bias, from information? Does that differ depending on the forecaster that you're looking at?
Maybe I'll let Marat. Marat, do you want to take this one?
So how do all these three components contribute to error? Well, that depends on the setting we are considering, right? So I guess in geopolitical forecasting, you can have one set of results. In, say, demand forecasting, you can have a different set of results. But in the Bean paper, we are looking at these geopolitical predictions from Good Judgment Project forecasters. And what we see there is that I think for most of the possible interventions that improve the predictive performance, most of that improvement could be explained by reductions in noise. So information and bias are also important, but noise, I think, captures at least 50% of the improvement in most cases.
Do you have a hypothesis in terms of why so much of it comes from noise? I know it's not talked about in the paper necessarily, but is that given the current news and media environment we have, where it's very much just stream of news and then sort of figure out the truth later, and so forecasters in today's age just have so much more information, so there's more noise in there. Is that something inherent in our decision making? Do you guys have a sort of hypothesis on that?
Just to fix ideas. So at this point, we only look at decomposing the forecasting performance into bias, information, noise. We don't really look into detail what explains each of these components, right? What explains the reasons for forming bias or information noise. So at this point, we can only speculate. And
Yeah.
this is probably what you're asking. So how can we speculate about that, right? I think one important feature of the forecasting errors is that the probabilistic forecasts often tend to be overconfident, right? Overconfidence means that your kind of probabilities are much closer to 0 or 1 than they should be. And this overconfidence can often be generated by noise. So kind of including irrelevant considerations into your probabilistic forecast. And then I guess a lot of these interventions do a lot to combat this overconfidence, right? So that you don't bet too much on these irrelevant signals.
Let me add to that. Can I add to that just a little bit?
Yeah, of course.
I think noise is also kind of, it's the end product that we are capturing with our model. And like Marat was saying, it's very difficult based on predictions alone to kind of go backwards and figure out the exact causes of this noise. But there's so many different sources that one could think of. You could think about mood swings. Sometimes I might be in a bad mood one day. Sometimes I'm in a good mood, but also in sort of like the sort of inherent noisiness in this sort of process that we go through when we convert these kind of inner hunches, you could call them, or the sort of knowledge that is somewhere in our brains into this one number that we then report as a prediction, right? That's a very complicated procedure, and there's just a lot of noise in that. but there's many different causes, and maybe it's the accumulation of all of them that we see.
Yeah, well, one hypothesis might be that the information universe is much smaller than noise universe, and that's how it might work. But that's a speculation. That's not something we have really good evidence for.
Saying that there's just a lot more, fake signals in that universe than real signals.
I mean, irrelevant, right? I mean,
relevant,
for any given event, you only have a very small number of things that really matter for that event.
Yeah, I think, one of the biggest things in improving the accuracy of forecasts would be to be able to predict the direction and the measure of noise in a given forecast. I know that that's sort of really hard to do, maybe even impossible right now, but, working towards that, and I think this model does that, is really interesting. And Marat, you sort of touched on this just now. Do you know of a relationship between information and noise? Is it proportional? Is it inverse? As the level of information increases, does noise increase with it, or vice versa?
That's actually a question that I was pondering a lot. But what I want to say is that in our framework, noise and information are kind of orthogonal concepts, right? So you could have all four scenarios: low noise, low information; high noise, high information; high low, and low high, right? Another perspective to consider that in our setting, forecasts are done by combining the event's intrinsic difficulty, so kind of the amount of noise, the size of the noise universe for the event, and the size of the information universe for the event, and a forecaster's ability. So kind of how, for example, a forecaster might pick out 90% of the information for the event and 10% of the noise, and that would be quite good forecaster. Or vice versa, 10% of information, 90% of the noise, and that would be quite bad. So what I would say is that essentially you can have all patterns of correlation. Correlation between noise and information. You could have events that could be very easy, very difficult, and that would essentially lead to different predictive performance patterns. So in our current work, we think that we consider forecasting groups that differ in ability, so their ability to pick out information and ignore noise, right? But we think that all events are of the same difficulty. So kind of noise universe has the same size for all event, and information universe has the same size for all event. And now we're working on an extension that could potentially also introduce difference between events in terms of difficulty, because obviously some are more difficult than others. So that would be my answer to the question: is there association between noise and information? And if it is, then how would it look like?
That's interesting.
And is there just a general relationship between, forecasters who have more information that generally have more noise? Is there any? Can you say anything about that right now, or no?
So do you mean that do forecasters who have more information tend to be noisier?
Yeah, for instance, absolute, in terms of absolute noise, say a forecaster has a 0.9 out of 1 in terms of information. Are they, generally just gonna have more noise than a forecaster that has, say, 0.2 information? Obviously, that's not to say who's better at forecasting, because there was all that gain of information. The gain in noise is unlikely to necessarily be the same, but as they're going up the information route, are they just happening to sample more irrelevant signals?
I would say the most straightforward example is super forecasters, right? And in our sample, I think compared to any other group, they are more informed, and I believe they're less noisier.
So they achieve both, but in terms of people that aren't super forecasters, right? Because they sort of check all the boxes. For a regular forecaster, if they're increasing their information, are they also increasing their noise? And that might be perhaps one hypothesis for why they're failing to, become a super forecaster. And it might then be better to sort of limit their information, because that would also limit their noise, because they're focusing more so on just the specific high impact signals rather than trying, to gain too much information.
I would say you probably want to consider it in the context of a specific intervention. So So what we do here, we are comparing two groups. Say, for example, untrained working individually with trained working individually, or untrained working individually with trained working in teams, with untrained working in teams, right? So in a sense, what you want to say is, does an intervention that increases information typically increase noise as well, right? This would be a question. But I believe that the teaming intervention increases information, but I'm not sure that it increases noise. I think it also reduces noise a little bit. So we're not sure if we have encountered an intervention that would do that in good judgment project. Maybe there were some results in the IPD study.
So let me add here a few things. So one thing which Marat already touched upon here is that there are lots of future extensions that we're looking forward to doing. One is to understand the heterogeneity of these bin components from one event to another. But then there's sort of another dimension, which is to say that, look, you might have 100 forecasters. Could we estimate the bin for each one of these individuals? Right now, we've written the initial paper. We're kind of, in many ways, in the baby shoes. So what we can do now is to sort of consider individuals as groups, right? So we can't separate based on individuals yet and make these kind of comparisons of seeing, does a regular individual has more information tend to have more noise as well? But certainly something that we want to do in the future. Now, one thing that I think is relevant here is in the follow-up paper where we analyzed not sort of these kind of training programs like we did in the initial paper, but we analyzed different ways to aggregate predictions as the treatment. There, what we saw was that there's certain aggregation techniques that tend to boost the amount of information, meaning that they're very effective in sort of finding the dispersed information in the crowd and returning an aggregate prediction that is even more informed than any one of the individuals. Now, one of the sort of takeaways there was that this is almost like what would I call it, a double-edged sword or a dangerous game to play, because the moment you start thinking about information, now you need to start figuring out what is information, what is noise, right? And when you make a mistake, when you interpret a noisy bit as information, that's called overfitting, right? And we see that actually in the paper. So some of these mechanisms that tend to be, or mechanisms that have the means to aggregate information or boost the information levels also have the danger of overfitting and increasing noise. So I think this relates to, Clay, what you were asking. Yeah.
I have a quick question. Something I've been thinking about just in the world of forecasting, like sort of an application of forecasting that I think is, has sort of gained some notoriety in the last few years, is when it comes to making decisions over bail for people in jail and sort of taking certain information about a person's sentence or their background, and then trying to make a decision over like what are the odds that this person is going to flee, like if they're a flight risk or not. Thinking through sort of the bin model, is this a case where maybe noise isn't the biggest factor when it comes to thinking about the accuracy of a forecast, and maybe it is like the actual information that you're using, and sort of going back to that question of what is information, I guess the question basically being like, can information be more of an important factor than noise in some cases when thinking about accuracy? Or have you seen that at all?
So let me actually, just recently, was it maybe a month ago or 1.5 months ago? Kahneman came up with this new book called Noise. And this is one of the topics that they talk about, in particular the noisiness in sentences like this. And they in some sense you can control for information, because every judge, suppose you have 100 different judges, they're all looking at the same case file, right? In some sense you're controlling for the information, but yet you got very different kinds of sentences. So where does that disagreement come from? It could be all noise. Perhaps they're extracting different amounts of information from the case file they got, but they argue that there's a lot of noise in that. Mm-hmm. Now, in going to your second question about the roles of information and noise and bias in finding accuracy, in some sense, it's hard to be accurate without any information, right? Right. So if you imagine an event, just to give you a simple example, suppose I'm predicting rain in a given city and it happens 20% of the time. So my base rate, sort of the naive forecast that doesn't add anything to today's prediction, will be 20%. I will keep on predicting that, right? And if I did that, I would have no bias, no noise, no information in my prediction. It wouldn't be very useful to the decision maker because I'm not adding anything that everybody don't already know. Now, if I add noise to that, it starts varying, but this is variability doesn't correlate with the outcome, so I'm actually harmful. If I add bias to it, I just shift it to like say 30%, right? But it's not until I start adding information that it starts actually becoming useful beyond just predicting that 20%, right? So in some sense, information is really it's necessary for being more accurate. And then noise and bias are just, bringing you back to just reducing your accuracy, right?
So I wanted to sort of, move ahead to the sort of second follow-up paper to the bin model of forecasting. This one is particularly interesting to us and probably a lot of our listeners because it focuses on crowd wisdom aggregators. A lot of people that visit Global Guessing, a lot of what we do focuses on prediction platforms like Metaculus and Good Judgment, and part of what they do is also aggregate their community forecasts. And sort of, first of all, could you just sort of explain what you guys were sort of testing with this crowd wisdom aggregator paper and what you found, and particularly discussing the unsupervised methods? There was one particular method that seemed to do the best out of the bunch, which was not only able to decrease noise, which all of the other methods did, but also increase information and decrease bias as well, which was the RBA one.
Yeah. So this was a follow-up paper where initially in the beginning of this podcast, I explained that the bin model really is a model of two groups, right? You have the control and the treatment. And the big question you want to answer is, how does the treatment improve accuracy by noise reduction, by bias reduction, and better sort of acquisition of information? And in the initial paper, we considered just different training programs and teaming and tracking, which led to the super forecasters. Now, in the follow-up paper, we realized that, well, we can sort of use aggregators as the treatment, right? And see how do different kinds of aggregators actually sort of reach the so-called wisdom of the crowds, right? There's so many different kinds of aggregators. We could take the median, the simple average. Now we have this kind of prediction markets and so forth. How do they do it, right? And so that was sort of what we went for here. And the main takeaways that we found was that averaging like techniques, so these would be measures of central tendency. So think about median, simple average, trimmed average, and so forth. They tend to boost accuracy almost exclusively through noise reduction. Now, actually, noise reduction overall was very, very important. It was the most important contributor throughout. But then we had some of these more sophisticated techniques like the RBA, which stands for the regularized Bayesian aggregator. I'll explain that in a second. And we also had something called the prediction markets. Now, these boosted accuracy actually through all the three bin avenues. Now, they did perform quite a bit better than averaging like techniques. But what I want to emphasize here is that little boost in accuracy comes at a cost, right? These techniques are quite a lot more complicated. Something like a simple average you can calculate on the back of your napkin. But then you think about the RBA method, for instance. This is a Bayesian techniques, requires quite sophisticated numerical estimation techniques that you certainly need a computer to do this. Prediction markets, on the other hand, require a lot of management. You need a lot of participants to keep the market liquid, much more complicated than a simple average. Now, as a final takeaway, we also looked at these prediction markets and we found that they were, among all these techniques, the most efficient way to harness information, particularly. But let me not get into that. Let me actually explain this RBA a little bit because it might be a little bit mysterious in the paper itself. Now, we don't explain it there too much because this is actually a technique that I recently proposed in another paper. This paper, it's called the Regularized Aggregation of One-Off Probability Predictions. Now, to describe it, imagine that you are in a task of aggregating a single set of probability predictions. Now, what this RBA really does is that it assumes that the disagreement that you see in the predictions come from two different sources, right? So it comes because the forecasters rely on different information about the outcome. That's one source. Or because there's simply noise in their predictions, right? Now, the disagreement due to informational asymmetry is what we will consider rational, okay? And it really offers an opportunity that we should harness. While on the other hand, the disagreement that is due to noise is irrational. That's what we call it. And it should be eliminated from the aggregation perspective. Now, the challenge here is that how on earth do you distinguish between these two different sources when you only have a single prediction per expert, right? It seems like a hopeless task. And it is challenging. And if you really think about something like an averaging like technique, it simplifies a lot. And it just says that, look, all disagreement is noise. Okay, we're going to eliminate it all and take a typical value in the middle. Now, this is a big lost opportunity because some of that disagreement actually could reflect private information, which we should then harness into our aggregate. So this kind of finally gets me to the punchline of the RBA. So how does RBA actually do it? What it does is that it uses this neat trick and it recognizes that rational disagreement is actually limited, whereas irrational disagreement is not. So let me give you an example. So suppose, for instance, I predict 0 probability for some event, but you predict 100% for some event, okay? Now, the event cannot both happen and not happen at the same time. So clearly, this disagreement cannot be purely rational. There must be some noise here. Okay, fine. What if I predicted, say, 1%, you predict 99%? Okay, this disagreement could be rational, but it's very unlikely that we both observed very strong yet completely contradictory evidence, right? So again, here, a lot of the disagreement is likely to be irrational, okay? Now, this is just to illustrate, but in the paper, what we can do is that we use mathematics and we can actually make this very precise and assign likelihoods to all possible compositions of the observed disagreement. So what does it do? So in machine learning, overfitting, I think I already touched upon this a little bit, occurs when noise is falsely interpreted as information. Now, RBA, which stands for regularized Bayesian aggregation, avoids overfitting by using a model that analyzes the disagreement in the predictions, and it allocates any excess dispersion to noise. So what's the net effect of this? It's an aggregator that, I guess, if it could speak, it would say something like, wow, there's a lot of disagreement here, much more than I would expect from purely rational forecasters. So let's be a little bit careful, right? And this is really what allows it to disentangle the two sources, harness a little bit of that private information, and that's what we see in the paper.
That's really interesting. I thought what was also interesting when you were talking about the other methods, particularly, I mean, for the unsupervised, because the other ones, I believe, were successful in reducing bias, is that they didn't reduce bias. And you would think that averaging would, if that's an individual sort of systemic over or underestimation, that over a given population, if it's large enough, that my bias should probably be inversely relational to someone else's. I mean, I guess, taking from good judgment is obviously a very specific sort of data set and with a very specific sort of identity of people that, were part of the geopolitical forecasting competitions and all of that. But do you have a hypothesis in terms of why, like, averaging does noise but not bias as well? Because you would think it would do both.
Marat, do you want to take this one?
Yeah, I would take this one. I would say in our framework, bias refers to kind of group level bias. So it's some bias that's shared across everyone. And in geopolitical forecasting context, I think one common bias is that people commonly predict that status quo would change, and this probabilities are typically higher than it would actually change. So basically, political environments are quite inert. And that was the point, I believe, made by Philip Tetlock in Expert Political Judgment. So you shouldn't expect a lot of change, but people still expect a lot of change. And in that sense, that's pretty common across all experts. So then when you average it, it still remains.
So do you think if you were to be able to have that bin model on an individualized level, which we'll get to in a little bit because that's something that I'm really interested in. Do you think in that case you would see averaging and the likes being able to reduce bias if you were able to break that down on a more, sub level?
Perhaps yes, if we have some kind of bias that is common to each of the person's level. But I think in general, kind of averaging can get rid of the noise since noise is averaged, right? And then, but by construction, it couldn't get rid of group level bias. So it might not even get rid of bias on the individual levels if people share some common source of bias, which might be the case.
If everyone's biased towards
Yes.
status quo change.
Yeah, it seems more like some kind of ANOVA decomposition. I don't know if it's a technical term, but essentially some of the difference in biases might be explained by variation across experts, and another could be explained by variation across events. We do not explore that at this point, but perhaps we could also look into that in the future.
I don't want to get too off track. I'm really curious about this bias piece. Like based on your findings from the bin model paper on bias, do you feel like some of those findings could be operationalized, as like a tool perhaps in like schools or even like a police station or just like these jobs where, people's bias is really relevant to the work that they do? Could this be a good way to sort of assess somebody's bias in different circumstances and different environments?
Let me give a few thoughts on that first, and then Marat can add. But because I was just recently thinking about this in the context of the RBA paper, actually, and I realized that in a lot of judgmental forecasting, I think the way it's done, it's almost like I'm giving you my hunch feeling about something, right? I kind of think about it for a little bit, and then I just give you what I think is my best guess. And I feel like we need to move away from that, and we need to work a little bit harder. And there's a lot of literature going back decades about this kind of reference class forecasting and talking about base rates. And I think we really need to start getting more into that, where we do not just give a hunch feeling, right? We really start thinking about reference classes, base rates, and it's work. I know, and that's why people probably don't want to do it, right? It takes a lot of work to look for similar cases and then evaluate some sort of base rate based on that. But I think we really need to start doing that more. And then once you have that base rate, then you start doing this kind of Bayesian updating of it. Now you think about, okay, this is the historical rate. What do I really know about the given instance that we're looking at right now? Is it unusually high or unusually low? And then you update a little bit. Now, why am I saying this right now? Because one of the possibly the best ways to reduce bias in predictions would be to educate people in this, to make them think about base rates and try to find more accurate reference classes and base rate and start from that.
And defining references classes could be very tricky, especially in the kinds of settings that we are considering, like geopolitical forecasting, since these are kind of one-off events, right? And to give you a sense of these challenges, Toby Ord, in his book, The Precipice on Existential Risks, tries to estimate the probability of human extinction from natural causes. But since no human extinctions has been observed to date, it seems like an impossible task, right? So you don't really have a reference class that is really defined tightly around the problem. And then his answer to that is that Toby's answer to that is that one could use data on other hominid extinctions like Neanderthals, or on extinctions of arbitrary animal species to estimate that. And obviously there is a very delicate balance on where to draw the line. So basically a very broad reference class might be kind of be overestimating or underestimating the probabilities, but a very small reference class doesn't allow you to estimate the base rate with any precision. So one has to strike the right balance in that. And that's, I think, one of the problems that makes reducing bias so difficult. And circling back to Andrew's question, could we use our framework to understand the individuals bias, information, and noise in making these very important high-stakes decisions, I think, yes, we can do, and probably the most straightforward application of this methodology is to evaluate different interventions that are meant to improve the quality of decision-making and, say, reducing biases. So, for example, we could test if a given training program really reduces bias, or if it doesn't.
So
no, that's true. That was actually one of the original motivations for developing this, is to understand what works and when, and where to go next, right? What kind of training program should we develop? It's almost like I like to say that, look, we have super forecasters, but could we create a super training? I hope so one day.
Yeah, Ville, you said something really interesting in your answer right there when talking about the need to do better with forecasting, go from sort of translating vague hunches into numbers and sort of doing some serious analytical work. And that's sort of what we try to do at Global Guessing, sort of really find out, what is the base rate? What are the key signals? How do we quantify it? How do we put all that information together? And, one of the big things that I got after reading the spin model of forecasting is that we should be more focused on the inputs of forecasting rather than the outputs of forecasting. If we could crowdsource base rates, if we could, I think in one of the footnotes you write that one interesting thing would be, getting individual sort of uncertainty about signals. Well, could we crowdsource signal identification and classification? So could forecasters work together to determine if something's a signal or a noise? And then could they work together to determine, is it then a positive or a negative signal? Could they work together to sort of come up with base rates and sort of crowdsource out all the inputs of the forecast, which would then conceivably help be able to reduce bias, increase information, and reduce noise? Do you see that as sort of being where forecasting should go, rather than aggregate just based on sort of very vague information to sort of, aggregate based on, clearly defined inputs? Because right now you're sort of going into the blind. There have been some papers out there, using natural language processing, pulling out forecaster rationales if they mention base rates. And you could even, conceivably leverage further NLP to even pull out those base rates. But for the most part, aggregators are more or less flying blind, relying on some NLP and some track records. So to bring it sort of back is, do you think that a promising future should be looking at crowdsourcing inputs of forecasting rather than outputs? Does that make sense?
Marat, do you wanna? I'm waiting because I think Marat probably is the right person to answer this one.
Yeah, I could start addressing this question. Is that I think one of the reasons why we consider experts instead of algorithms for geopolitical events is that it's pretty difficult to understand what the inputs should be and how they should be gathered, and what is relevant and what is not. So in some sense, if we ask experts for their predictions, we delegate this very difficult process of gathering information, modeling these events, to experts, right? And then they could probably do better than any of us in doing that. What you're saying is that it would be good to curate the inputs, right? Somehow.
Well, not only just that, but like, right, if you're getting your experts to not only get their output, but get their input. So then, yes, like you have, 15 different forecasters' base rates. And so you're actually aware of what's going into their output, not just getting their end result.
Oh yeah. So one thing is, should we elicit more from people? So I think it has advantages and it has disadvantages. So an advantage, of course, is that we're getting a lot of information on their thought process and they're following a more structured process. But a disadvantage is probably we might not know how to best structure this elicitation process. So probably some of the super forecasters might know it much better than we do. And another disadvantage is that it puts a lot of cognitive load. It might be a quite tasking problem, quite taxing request on the time. So the more we ask, the less people spend, the more we ask people to explain their rationales, the more time and energy they have on actually coming up with forecasts, right?
Yeah. I mean, I guess my counter would be, as Andrew and I do these sort of in-depth forecasts, like we're doing the same sort of calculate base rates, add in all the signals. In some ways, actually having that, structured and having, clear places to put it would in some ways decrease our cognitive load.
I would agree that this would be fascinating. So if we could get a look under the hood of how this process is structured, we could have a much better understanding of what explains bias information noise. And at this point, I don't think we have a lot of high quality data on which to do research, but going in the future, it can be the key to understanding better forecasting practices.
And like I sometimes like to make these very simplified comparisons between a human forecaster and machine forecaster. And I like to think that, ultimately, both could be modeled in very similar ways. In many ways, we could be viewed in a very simplified terms as just some sort of functions that are trying to convert a bunch of information into a point prediction, right? And there are a lot of advantages and disadvantages to using one or the other. In many ways, if you can use a machine learning model to make your prediction, you probably should over a human forecaster. But there's just a lot of context that are almost unique, like very unprecedented kind of questions that we would need predictions for. And we don't really have a lot of data to train machine learning models to make predictions for. And this is where humans tend to be very useful, having expert predictions. And it's interesting to just kind of play with these kind of questions and then think, why is the human function able to make a prediction there? And in many ways, we've been sort of training our model the entire life, right? You have this sort of life experience, which is your training data. And you're sort of reaching out from a lot of different kinds of, or similar kind of cases you've seen in the past. And then using that as a bridge to predicting this new kind of case, right? Now, machines are not really able to do that because they're very specific. But at the same time, humans can do that. And the process of doing that is just very, very complicated. Like the information processing that is going in that, I mean, who knows how exactly that works, right? So it might be that we can ask people to write down all those rationals, or we can elicit all kinds of other quantities from them. But in my opinion, at this point, that's just a tiny glimpse of all the sort of signals and noisy bits and whatnot that actually go into that function that pops out that probability prediction, right? So I think it's exciting too, but it certainly has a lot of challenges of trying to go after that input. I feel like a lot of people would not be even able to articulate, even given as much time as possible, the exact reasons why they believe in their prediction. It's very difficult, right? But there are some things that you can do here. In particular, we have all these kind of Delphi methods where we allow people to discuss and argue. And in particular, in the bin model, we saw that the teaming is a very effective way to boost predictions, right? Even if everybody's making their own predictions. And one reason is that this allows people to exchange ideas, right? Their signals, their inputs, right? And argue about them, which would then allow them to disentangle what is noise and what's not, right? And another sort of loop back here is to this idea of a function in our heads that is trying to make predictions, right? And we make this case in the bin model where we say that discipline and sort of rigor in your thinking process is very crucial to reducing noise. And possibly this is why we see super forecasters being so good. So from like a machine learning perspective, I like to think about these guys as being very honed, right? They've had lots of data to train on. They know what the parameters are, and they can make very accurate predictions, okay? These are just very simplified thoughts, but sometimes I find these very helpful when I'm thinking about the connections between machines and humans.
Andrew, you're muted.
Sorry. So going back to something that you both were talking about a bit earlier with respect to prediction markets, I was wondering, why do you think prediction markets are so effective at increasing information? Like, what do other forecasting environments, like some that we've talked about, Metaculus, Good Judgment Open, what do they get wrong? And is it that there's too much friction to share information, like we were just talking about, between the actual having a forecast and inputting it into the into the platform?
Again, I would like to recap that we don't really look in that depth. So again, we'll have to speculate about that. But my best guess would be that first, prediction markets provide the participants with better incentives to come up with a good forecasts, right? Since this is essentially trading, and the result of your forecasting process is linked to some of your monetary incentives in some sense. And second is that prediction markets might allow for a more efficient exchange of information and build up on information. Since, well, in poll-based settings, the way that the information exchange is structured is left to the participants. So they can decide to share information or not to share. They can decide to tell themselves different things or not. But in prediction markets, all the information will be aggregated into price by construction. So I would guess that these would be the two reasons that would explain the success of the prediction markets. But again, that's mere speculation at this point.
There's actually, now this kind of reminded me, there is an interesting paper that Pavel Atanasov and a bunch of others from the Good Judgment Project wrote on comparing sort of prediction polling done right compared to prediction markets. And they actually find that you can get a little bit of an accuracy boost by doing all these right things, like extremizing, differential weighting, all these things on predictions collected simply through polling, right? You get a little bit of an edge on prediction markets.
Yeah, and prediction markets were especially better closer to the event than the polls. I think the further out you were, the more equal they were in that paper. I think so. We have just sort of one more quick question, and then you guys, before the end of the show, are going to have to do the rapid fire round of this podcast, which you will be asked to make 4 forecasts in short order. But before we get there, sort of just one last question that I had about the bin model, or sort of what you write, is that when you sort of introduce training about sort of probabilities, that getting better at recognizing betting odds reduce the noise of forecasters because they got more consistent. And I was just sort of wondering if you had a hypothesis in terms of why that effect was happening, like how knowing the odds helps you sort of reduce the noise going into your forecast. Is it, understanding, if you know what 75% is, then and if you understand the difference between, say, a 75% likelihood and an 85% likelihood, that you're more hesitant to sort of increase your forecast further, and so you're less likely to sort of draw in irrelevant information, or if you have some sort of other hypothesis in terms of how that's working, because, just having a better understanding of probabilities doesn't, at least right away, indicate why that would sort of reduce their noise in terms of processing signals.
My response to that would be that noise makes you believe that you have more information than you actually have. And because of that, you're making more overconfident predictions, closer to 0 and 1. But if you're trained in probabilities and you understand the geopolitical forecasting setting, you would probably do better than that. You would understand that if it seems that it's a sure bet, then something is wrong. And then it means that you would correct closer to the base rate. And that would tamp down on noise.
That makes a lot of sense. That makes a lot of sense. Ville, anything you'd like to add, or you ready to make some forecasts?
No, I think Marat is a spot on. So let's make some forecasts.
Alrighty, you guys are gonna have 4 questions to forecast. Even if you have no idea, you'll have to still put out some sort of number here. There is no weaseling out. All of these questions are ones that all guests of the podcast have been made to give, and all at different times in there. So it'll be interesting to see who gets them the most correct once they resolve. And if at any point you want to change your forecast, feel free to reach out and change them afterwards. So the first forecast is, what is the likelihood that Russia annexes territory in Eastern Europe by 2026?
Could you repeat it one more time? Sorry.
What is the likelihood that Russia officially annexes more territory in Eastern Europe by 2026?
Does Ukraine count?
Yes, further annexation of Crimea obviously is already passed.
Um,
So how we're gonna do this? Should me and Marat say it at the same time?
How about, we'll flip who forecasts first. So Ville, you'll go for this question. You'll go first. Marat, you'll go first for the next one.
Okay. 2026. I say 3%.
I'll say 20%.
So this is a good example of information here, right? You're asking a Finn and a Russian, right? So
Okay, perfect.
Yep. Do you want to take the second one, Andrew?
Sure. The second question is, what is the likelihood that we are to find alien life by 2030? And alien life can be, a single cell organism, sort of any type of like living organism.
Techno-signatures and evidence of past life as well, as long as it's not originally from Earth.
I'd say
2030 was.
Yep. Marat, 10%.
I don't want to be lame and say 3% again, so let's make it 2%.
All right. What is the likelihood that there is an Olympic boycott of the Beijing Olympics in 2022 by a majority of the Quad and the Five Eyes, which would be the US, Australia, New Zealand, the UK, Canada, India, Japan, and am I missing one, Andrew? I always, you think at this point I would remember who all the Quad and the Five Eyes are.
I think that was all of them.
Yeah. We'll say that's all of them. So what is the likelihood that a majority of those boycott the next year's Olympics in China?
20%.
20%.
10%.
Interesting.
And then finally, the last question is, what are the odds that Saudi Arabia and Israel normalize diplomatic ties by 2025?
20%.
What did he say? What did you say?
20%.
Oh, I heard 100%. I was like, wow, after all that thing you said.
I know, the whole podcast just...
Are you sure it's not 99?
Yeah, exactly. Okay. What would I say? Say 25%.
Interesting. Well, that's great. We will let you guys know in 2022, 25, 26, and 30 how those panned out. We'll give you guys your Breyer scores. So maybe you guys are very omniscient, or perhaps making a rapid forecast years in advance won't turn out to be the most accurate down the line. We'll just have to see. Before we go, what is the next research that you guys are planning to do with BIN? You guys have sort of hinted at that, what you've done with BIN is only the start, which is great because I think it's a very interesting model and so promising for future research. So yeah, what are you guys thinking about for, digging deeper into BIN down the line?
So I mean, there really is so many different directions. One direction is, like we mentioned already, to make it a little bit more flexible in terms of how we treat events and individuals. So as of right now, the initial version of BIN considers 2 exchangeable groups of forecasters. What we want to do here is to allow it to consider heterogeneous individuals, so we can estimate BIN for each individual. Maybe we'll allow the BIN also to change from one event to another. And there are different ways we could go about doing this. One is that we could also try to incorporate some covariates, right, into the model. So, the individual's gender, education level, and so forth. Same thing for events. What kind of area of question it is, does that matter? Another idea is to move away from binary predictions. So probabilities of binary predictions. There's a lot of questions out there where we actually want a continuous prediction or the continuous outcome. So I don't know, Marat, what else we have on our plate?
I would say most of the stuff we are doing would allow us to take BIN out of the narrow context of geopolitical forecasting and to other contexts. Say, we could probably try to analyze macroeconomic forecasting with that, because in the macroeconomics, you have a lot of dependence in the cross-section between different variables and over time. And for that, we need to extend our model, right? I'm also thinking of importing some of the ideas that we developed with Ville in this BIN model paper into my research agenda on new product forecasting, which I'm also currently working on. So I would say this paper could break a lot of new ground for many different applications. And apparently, from what I heard from Ville, there is some demand from other researchers for access to our model, and we have this R package BIN tools that other researchers are going to use.
Yeah, so it'll be exciting to see how people end up using it. You know, what kind of BIN analysis we find.
Yeah, I'm considering using the BIN model, the R package, in a future research project down the line. So I'll definitely circle back with I'm sure questions in terms of how to operationalize it best. But yeah, I think it's very exciting. And Marat, when you mentioned doing economic forecasting, and the difficulty in sort of specifying all those signals with geopolitical forecasting, I would imagine in the economic domain, there's a lot more opportunity for actually specifying and, clearly identifying signals when you look at how economic forecasting is done right now versus, sort of the current questions that you would find on Good Judgment or Metaculus or whatnot. So that'd be very interesting. Where can our listeners sort of find both of you guys, keep up with them? We'll obviously be more than happy to share out the next papers that come out with BIN and discuss them with you guys when they happen. But in the meantime, where can people sort of keep up with the work that you guys are doing?
On my website, maratsalikhov.com. Just my name and surname.
And then Ville?
Same for me. I mean, you could just come to my my website. I do actually update it quite frequently. So you can see all the links to all the papers, R packages, everything you can see there. But I also do try to, whenever something actually comes out, right? It's either published or we put up a new revision. I try to post these usually on LinkedIn, Twitter. Twitter is a great place. So if you want, I think that's probably the right answer on my end. Like, if you really want to keep up with the updates on this space, please just follow me on Twitter and you won't miss it.
All right. You guys that are listening to the podcast now will be able to find those links in the description to find both of those. And yeah, Ville, Marat, it's been an absolute pleasure to have you guys on. Thank you for so much of your time and for discussing this paper. I thought this was phenomenal and very interesting. And so thank you so much.
Yeah.
Thank you. Great
Thanks
pleasure
a
for me
lot.
as well.
Yeah, thanks a lot, Andrew and Clay. This was really fun.
All right, and this was the 16th episode of the Global Guessing Weekly Podcast. Thanks so much, everyone. Bye-bye.